So in this video, we're going to be discussing chapter 4 and section 4.6, and that's the arrangement of electrons in energy levels surrounding the nucleus. So electrons are arranged in a very specific manner at specific levels of energy that surround the nucleus. But before we get to that, we have to talk a little bit about just electromagnetic radiation and the energy waves. All right. So electromagnetic radiation is basically energy. All right. The particles that are moving as waves of energy. All right. And so those waves have got peaks, and the distance between those peaks is called as the wavelength. Okay. And either those waves can occur very frequently. That means they are high frequency, which means they are high energy, short wavelengths. Or they can have lower frequency. And that means that between those peaks there are longer wavelengths, which is low energy. All right. So high energy would be X-rays, UV rays. Low energy would be something like the infrared rays, microwave, etc. All right, so as you can see here, this is barium, and a lot of these elements, when you do a flame test, that is, that you subject it either through to light or a flame, they give a characteristic color. So you're heating up this element, and then you're passing that light that it emits through a prism, and then when the prism will split that light coming out, and then you'll see a line spectrum. All right, so this line spectrum is very characteristic of atoms. Atomic spectrum is different from what we know as the continuous spectrum, the visible spectrum that we see, which is a continuous spectrum of light that we observe. Whereas the atomic spectrum is like a discontinuous spectrum. So you see them as lines, and there's this dark spaces between the lines. All right, these lines, distinct lines, represent the energy difference between those energy levels around the nucleus, in this case of the barium atom. All right, so each element has its own unique line spectrum. And from the data collected from line spectrum, the theory or the theory, I guess, is what would be an appropriate word, about how these electrons are arranged, the quantum theory about how electrons are arranged around this nucleus within the atom. So these lines in the atomic spectrum are associated with the change in energies of those electrons as they're moving from one region to another. And each of those regions or energy levels, to be more appropriate, has a specific energy associated with it, right? So those specific energy levels are labeled as the principal quantum number. All right, quanta being a packet of energy. All right, a certain fixed amount of energy. So when you say that the energy of the electron is quantized, meaning they have a very specific energy value. All right, so the principal quantum numbers, or the energy levels that are labeled as the principal quantum number, range from and they're given the symbol n, and they range from n equals 1, n equals 2, n equals 3, n equals 4, and so on. All right, so as that n value increases, that means that principal quantum number, or that particular energy level, increases in energy. All right, so n equals 1 is the lowest energy level, and as as the value increases, that means it has more energy level. This is the closest one to the nucleus, and the furthest one away from the nucleus has the highest energy. Okay, so electrons which are further away from the nucleus have the highest energy. You can liken this to a lecture hall where, for example, at the bottom rung, at the bottom, where the podium is and the speakers are standing, it's the lowest potential energy. But as you walk up the steps further away, the potential energy increases. All right. So at the furthest away from the bottom would have the level that is furthest away from the bottom would have the highest energy. It's the same principle. Okay. So as you can see here, the electromagnetic spectrum is a continuous spectrum, unlike the atomic spectrum. So here you have regions where you can see that the wavelength is longer. So wavelength is this distance between this peak and this peak. All right. Okay. So it's less frequent. All right. So that's why the wavelengths are longer. Whereas when the frequency increases, you can see that the wavelengths are shorter. All right. So shorter wavelengths means higher energy. All right. Like opposite. Longer wavelengths mean less energy. All right. Okay. And so UV, X-rays, gamma rays have very high energy, which is why they're very destructive, whereas microwaves, infrared, and radio waves are less harmful, as they have less energy. Okay. Now, visible light falls in between here. All right. So it's neither high frequency and it's not low frequency. So the wavelength is also in between the long and the short wavelengths. Okay, so if you look at the wavelengths in meters, you can see that between 10 power negative 7 meters to 10 power negative a little less than 10 power negative or a little greater than 10 power negative 8 meters is where the visible region is. So 400 to 700 nanometers is the equivalent in nanometers. That's where the visible range is. All right. So again, beyond the 700 nanometers, then is the ultraviolet region and so on. Okay, so that's a very narrow range, 400 to 700 nanometers. All right, and then if you go, beyond 700, you're in the infrared region, and if you go less than 400, then you're in the ultraviolet gamma rays. Okay, so as I said, you can even liken these energy levels to like a bookshelf. So n equals 1 is the closest to the nucleus. It has the least amount of energy. And then as you go further away from the nucleus, like climbing a ladder, the higher you go, the more energy, because you have more potential energy in case of the ladder or the bookshelf. So that same concept analogy can be applied here, as n equals 5 has the highest principal quantum energy compared to n equals 1. This is just a rough diagram showing the analogy between the electron energy levels and applying it to like the planetary system. So if you imagine the nucleus to be like the sun, and if you imagine that these are the pathways around which just like the sun, all right, these are the planetary pathways around which these electron energy levels are arranged around that central nucleus. So that's a very simplistic analogy, but it works quite well. All right. So you have n equals 1, that's closest to the nucleus. It's got the least amount of energy. N equals 2 is the next, n equals 3, and n equals 4. Now the other thing is that when you have the least amount of energy, electrons means energy, all right? So if this particular energy level has the least amount of energy, it can't hold a lot of electrons, and it doesn't. It only is able to hold 2 electrons. N equals 2 has a little bit more energy. It's able to have a total of 8 electrons. And then n equals 3 has more energy, so it has 18 electrons. N equals 4 has, at least here, has the highest energy, so it's able to hold 32 electrons. Okay, so the more electrons an energy level is able to have, that means the more energy it has. Okay, now these numbers are not by accident. N equals 1 holds 2 electrons, all right? Period 1 has got 2 elements, hydrogen and helium. N equals 2 has got a total of 8 electrons, all right? That corresponds closely with periods 2 and 3 in the periodic table, which have 8 elements. And then N equals 3 has 18 electrons. That corresponds with periods 4 and 5, which have 18 elements. And then N equals 4 has got 32 electrons, and that compares with period 6, which has 32 elements because you have the lanthanides. Period 7 has, it should have had 32, but it has only 29, and I explained why that is the case in the previous video. The other thing to take away from this diagram is that within these main energy levels, the principal quantum number, you have what is called as sublevels, all right? Those sublevels are given the labels of S, P, D, and F, all right? Okay, so n equals 1 has one sublevel, S. N equals 2 has two sublevels, the S and the P. N equals 3 has three sublevels, S, P, and D. N equals 4 has four sublevels, S, P, D, and F. So the number of sublevels numerically is equivalent to the number of the principal quantum number, all right? Within the sublevels are regions called as orbital. That's where you have the highest probability of finding the electrons, all right? So if you imagine that orbital to be like a box, all right, like you have here, all right, and each box can hold only 2 electrons, okay? So that's why you have just 2 electrons in n equals 1. Now here you have 4 boxes, so each box can hold 2 electrons, so 2, 4, 6, and 8, okay? This has the 4 plus another 5 from the D sublevel, all right? So it has a total of 2, 4, 6, 8, 10, 12, 14, 16, and 18, okay? And then here, of course, you have 7 of these boxes from the F sublevel, all right? 7 of these orbitals, to be more precise. And so the electron count can go up to 32, okay? The other thing is that when there are 2 electrons in an orbital, they are not aligned in the same way. So one is aligned north-south, the other one is aligned south-north. So they have what is called as opposite spins, okay? All right, we'll continue this in the next video. Where we talk about energy levels a little bit more further and then conclude this section.